Yes, now we look at how AI turns words into coordinates. We already saw right from the very beginning that computers do not recognize words, but we have found a way to translate words into numbers, into coordinates, and all of that, and then computers can make sense of them. So let's go ahead to look at that, how AI turns words into coordinates. So here, humans naturally understand language. Of course, it's our thing to understand languages as human beings, right? For example, if we say the cat sat on the mat, a computer cannot directly understand these words, but it only processes numbers. So modern AI systems solve this problem by converting words, phrases, sentences, and documents into numerical coordinates. So these numerical representations are called embeddings. So when you hear about embeddings, it is uh, us numerically representing words in numbers, numerically representing words, that's embeddings. So embeddings allow AI systems to understand semantic similarity, perform search by meaning, recommend content, translate languages, and answer questions. So we can then retrieve relevant documents also and generate text. So the central idea is that AI represents meaning as location in a high dimensional space. So AI represents meaning as a location in a high dimensional space. So we move on to talk about from words to coordinates. Now we know about coordinates in geography, right? We know about latitude and longitude and all of that. If you consider a map, cities have coordinates like Tokyo has a latitude of 35.6764 and longitude of 139.6500. Paris has a latitude of 48.8566 and a longitude of 2.3522. New York has a latitude of 40.7128 and longitude of -74.0060. So AI creates a similar map for language. So instead of cities now, we can now have maybe you have cat. So cat has coordinates 1.2 -0.5, 3.7, dog 1.5 -0.2, 3.8, car -2.35.1 -1.7. Now, words with similar meanings tend to be close together, while words with different meanings tend to be far apart. Okay, that's us creating coordinates for words now, which that's like the process of embedding like that, assigning numerical values to words, so to speak. Now, the question is, what is a vector? We learned about in the last video, we talked about mathematics pathway for AI engineers, right? And then we saw that with the usefulness of vectors. So a coordinate list is called a vector. So when you have a coordinate list like this, that's actually a vector. This is like a row vector now. So a coordinate list is called a vector. For example, if you assign, these numbers are it's not, but when you saw cat here, it doesn't mean that everywhere you see cat, you must always see this. So we can also have cat here to be 0.23, 0.88, -1.45, dog 0.31, 0.80, -1.39. So each number is called a dimension, right? So each number is a dimension. So the individual dimension usually do not have a direct human interpretation. So they may not mean much to a human, but they mean so much to a machine because humans read words, machine reads numbers. So we have to find a way of turning our words to numbers for machine to understand so we can then have a communication. So it's like embeddings help us to bridge the gap between human language and machine language, so to speak. So each number is called a dimension. So the individual dimensions usually do not have a direct human interpretation. Meaning is stored across the entire vector. Now, question, why coordinates capture meaning? Suppose AI repeatedly says the cat drank milk, the dog drank water, the kitten drank milk. The words cat, dog, and kitten appear in similar contexts. As a result, their vectors become similar. This follows a distributional hypothesis that words that appear in similar contexts tend to have similar meanings like that, right? So while cats are not dogs and dogs are not cats, you can almost hardly think about cat without thinking about dog, right? Because in our civilization, we have always associated these two words together. Do you like pets? The first, probably you have you almost always first thinking of cats and dogs. So, and then we have the old approach. So for the old approach, right, before embeddings came, we had one hot encoding approach. So before embeddings, words were represented using one hot vectors, and in that case, we still use one hot encodings in machine learning these days, especially when you're dealing with categorical data. So if imagine your vocabulary, you have cat, dog, and car, and the representations are for cat, you just say 100, dog 010, car 001. So that's one hot encoding. The problem with this is that the computer sees no relationship between cat and dog because they are just on their own, so to speak. So every word is equally far from every other word. So cat is as far away from dog as is as far away from as dog is far away from car. So normally, right, in the modern context, cat and dog are closer together than car is to either of them. So, but in the case of using one hot encoding, before we started to use embeddings, every word is equally far from every other word. So when we talk about one hot encoding example, distance is often measured using Euclidean distance. So for vectors A and B, right, the distance between A and B is simply calculated as the summation over I of AI minus BI all squared, you know. So if you compute these distances now, imagine for one hot encodings, you have 100, 010, 001. So to do cat dog now, so you have linear algebra, take the norm between cat and dog, and then you take between dog and car. So cat and car, in fact. So you see cat and dog 1.412, that's square root of 2. Cat and cat, still same thing because there is equal distance happening there. So the output we see is 1.4, 1.4, 1.4, 1.414. So the computer believes that the distance between cat and dog is still the same distance between cat and car, and that's not true. This is clearly not true semantically, because a cat is closer to a dog than a cat is close to a car. Then we then have dense embeddings. Modern AI uses dense embeddings. For instance, for a cat, now we can then have something like 0.8, 0.7, 0.1, and they are close together. For dog now, 0.8 is not too far away from 0.9. Then 0.7 is really close to 0.6, 0.1 is close to 0.2. And then car, of course, is now totally far from them. So minus 0.5, 0.1, 0.8. In this case now, similar words have similar coordinates. I don't even remember running this code. I think I should have run that. Yeah. So, um, now, because the way this thing is now, similar words have similar coordinates. They have coordinates that are close by. So that by the time you compute the distance between the distances between pairs of words, you don't just get equal distances. You get distances based on how close together the words are. So here now, cat and dog is now 0.1732, while cat and car is 1.5937. So you have some distance between these words now. So it means that cats are more related to dogs than cats are related to cars, like that. So the output we got there, like you saw, is this now, that the distance between cat and dog is less than the distance between cat and car, which better reflects meaning. And that's the blessing of embeddings compared to one hot encodings that were used before we began to do this. So imagine a semantic map now. You have tiger, you have lion, you have cat, you have dog, and then you have car. So a lion is closer to a tiger than a lion than uh, a tiger is closer to a lion than a cat. But of course, a cat is also close to a lion. Then a dog is closer to a cat than you have all of that, and then a car is far away from all of them. So you discover that nearby points represent related concepts. So lion, tiger, cat, dog, they are really close. So distance corresponds to semantic similarity. So the closer they are together, the more semantically similar they are, the more close in meaning they are, or close in usage, so to speak. Now, how AI learns coordinates now. So coordinates are not manually assigned. They are learned from data. So AI learns coordinates from data. Suppose AI sees the cat drank milk, the kitten drank milk. So you might have been wondering that, oh, how do I get to know that this is what I should be assigning, right? So AI learns it from data. You don't have to worry about that. So coordinates are not manually assigned. They are learned from data. Suppose AI sees the cat drank milk, the kitten drank milk, and the dog drank water. The model adjusts vectors so that words occurring in similar context move closer together, and this process is performed using optimization and gradient descent. So you see where the optimization and gradient descent comes in. So it sees how often how close together the words are and how closely related they are and then it uses that as a basis for judging what the coordinates should look like. So the process is performed using optimization and gradient descent. And then we have word to vec. One of the most influential embedding methods was word to vec. So the core idea is you predict neighboring words. Example sentence, the cat sat on the mat. So inputs you have cat. If you now input cat, so the target outputs are D and sat. Okay. So if a word consistently appears in similar contexts, it receives a similar embedding. Receives a similar embedding. And then we have the skip gram model. So the skip gram predicts surrounding words from a center word. For instance, if you say cat now, from the original thing, the cat sat, right? So D before, sat after. So the skip gram predicts surrounding words from a center word. So if you have cat, then the target will be the D and sat because the cat sat, right? So the training objective is the fact that the probability of context given the word. So you want to know the probability of the context given that word. So when I mention cat, am I talking about the fact that the cat is sitting on a mat or something like that? So the model learns embeddings that make context prediction easier from the data for sure. So we then have continuous bag of words, CBOW. CBOW reverses the problem. So instead of having to predict words surrounding a word, you then have something like the dash sat. So, and then the prediction is cat, right? The training objective in the case of continuous bag of words is this probability that you get the word given the context. So you're talking about something sitting, right? So what sits based on all the information that has been available to the AI? The training objective is what is probability of the word given the context. So with continuous bag of words and skip gram, both continuous bag of words and skip gram produce useful embeddings. So depending on whatever you like, but then we have the idea of embedding dimensions, which are game changers. So real embedding vectors are much larger than 2D or 3D. So typical sizes for word to vec, you have 300 dimensions. For glove, you have 300. For BERT, you have 768. For GPT embeddings, you have 1536 plus and all of that. So example, you have 0.12 minus 0.34, 1.56, and so on and so forth, up to 0.91. Each coordinate captures part of the word's meaning. Okay, so you have a very large embedding that can actually, so the longer the embedding is, seems to mean that you're going to get something more accurate. Then we have sentence embeddings too. It, entire sentences can also be converted into vectors. For instance, you have a sentence, I love pizza. That can be embedded as 0.445 minus 0.71, 0.12, and so on. So the vector then represents the overall meaning of the sentence, right? So we also have semantic similarity. So for semantic similarity now, imagine that, consider this sentence A, I enjoy pizza, and sentence B, I like pizza. Sentence C says the stock market crashed. Totally unrelated with these first two sentences. So we're talking about semantic similarity. I enjoy pizza and I like pizza are semantically similar, but the stock market crashed is totally far away semantically from all the first two sentences. So embeddings for A and B will be very close, but embedding for C will be far away. This enables semantic search. And then we have cosine similarity, which I think I mentioned in the last video. I think we've seen something close to this before. And this is basically the idea of vectors. That's a vector multiplication, the vector dot product and things like that. So dot product basically. So the most common similarity measure is cosine similarity. So if you have vectors A and B now, the cosine similarity is A dot B. So it's more like you have cos theta, the angle between A and B, the more like the distance between A and B angularly is actually A dot B over the absolute value, the modulus of A multiplied by the modulus of B, where A dot B is the summation of AIs and BIs. That's simply dot product. And A is the modulus, which is square root of the summation over I of all of the AI squared. So values range from 1, which is that. So when you have 1, that's identical direction. When you have 0, it is unrelated. When you have -1, that is opposite direction. So more like what we think about when we talk about correlation. And then you can actually run the code here. So you have A to be 1, 2, 3, and you have B to be 1, 1, 2, 2. So the cosine will just be dot of AB, that's 1 times 1 plus 2 times 2 plus 3 times 2, all over, the modulus of A and modulus of B. So, and that gives us 0.9799. So they are really, the words are really close. That's 0.98. That's the output. If I change this to 3, you're going to get a perfect cosine similarity of 1. So you see 1 here now. So, but this is 2. So you get that. That's 0.9799. That's 0.98 in short. So the vectors point in almost the same direction. Therefore, they are highly similar. Okay. So imagine if you had like 0, 1, 2. So this 0.98, you won't have this 0.799. You're going to have something way smaller. That, or maybe not way smaller, 0.94. Okay, what if I have 0 here, like this? Okay, so you see it's seriously degraded. So they are far apart now. So, but initially we had 1, 2, and 2, like this, and then this goes. So the vectors point in almost the same direction, therefore they are highly similar. Now, question is, why do directions matter? We are talking about how AI turns words into coordinates, right? So consider that A is 1, 2, and B is 2, 4. Notice that B is 2 times A. The point, they point in exactly the same direction. And that's where in linear algebra we say they are linearly dependent. So it means that B doesn't give us too much information compared to A because they're basically in the same direction. So the cosine similarity in this case will just be 1, because they're basically in the same direction. So even though the magnitudes differ, this is why cosine similarity is often preferred over Euclidean distance. So that for Euclidean distance, you don't get cosine similarity tells you that, oh, these two, though the magnitudes are different, but they are basically pointing in the same direction. Now we talk about contextual embeddings. Older systems assigned one vector per word, right? So for bank, the problem, example bank. So you can have river bank or bank account. So when you hear bank, it can be river bank or bank account. So different meanings require different representations. So modern transformers solve this issue. Instead of assigning one vector per word, so, and then we then begin to talk about context-sensitive meaning. You have sentence 1, I deposited money in the bank. I deposited money in the bank. Sentence 2 says, we sat on the river bank. The word bank receives different coordinates in each sentence. The embedding depends on context. This is called a contextual embedding. So so the AI doesn't just give you bank for the fun of it. It gives you bank when it sees the context. The context you're in will really matter in that case. So, or maybe the first word I'm typing in the system is bank. So it needs to be sure what kind of bank are we talking about here, right? Then we go on to talk about transformers. Models such as GPT and BERT use self-attention. So we talk about attention involving the KQV stuff. So every word examines surrounding words, and instead of assigning a fixed meaning, the meaning is a function of the context. So the resulting embedding becomes very dynamic. So you can say bank, and in the context, it's thinking of riverbank. You can say bank in another context, it's thinking of bank account because the context is really important in transformers. Then the question is how ChatGPT processes data text. Second video in this playlist was totally dedicated to how ChatGPT is a probability machine. So suppose the user writes explain black holes. So the pipeline will be something like this. So it starts with text, right? And text become tokens. The tokens are embedded, and then we have transformer layers, and then we now output the embeddings, and it then gets out our predicted tokens. So, and that is where it's now start to explain black holes. So each stage operates primarily on vectors. So the text input is the explain black holes now. So these explain black holes are now broken down into tokens. Maybe it's gonna be like explain black holes like that. And then each of those tokens are then embedded, and then they pass through transformer layers, and then they are outputed, and then you have the predicted tokens. So then the tokens are coming together again to answer your questions. So each stage operates primarily on vectors. And then we have the idea of retrieval-augmented generation, RAG. So many AI systems store embeddings of documents, right? So because many AI systems are trained on, most of the materials, that are available to humanity, right? So many AI systems store embeddings of documents. For instance, doc A is physics, document A is physics, document B is history, document C is medicine, and then you now give a query. What causes black holes, right? So the query is embedded into a vector. This query, what causes black holes, is embedded into a vector. Then it will now look for the nearest documents that the nearest document to black holes will be retrieved. Obviously, this will be about physics now because we're talking about black holes. So nearest documents are retrieved. Then the language model then uses those documents to generate an answer. So it sees, okay, what causes black holes? So it quickly does some search and looks like, oh, black holes should be something in physics, not history, not medicine. Then it picks physics and then it uses the information available on black holes there to answer your problem, your question. So the language model then uses those documents to generate an answer. So we have a RAG example here, simple example, by the way. So cats are pets. That you have three documents here. Cats are pets, dogs are pets, and you have black holes warp space-time. And then the query is, what are black holes? So the process, it will embed the query, right? So but break them into tokens and embed them, and then pass them through transformer layers, and you have your output embedding. So embed the query, embed every document, then compute similarity cosine scores. So it is embedding this, it is embedding the document, and it will now see how similar they are. Then you now compute similarity scores, right? And retrieve the closest document. So because everything is embedded, so probably to already have seen black holes. So that shows some similarity. So the physics document will retrieve the highest similarity score for sure, because you're dealing with black holes, right? So imagine this now that you have your query is embedded at 0.9, 0.1, and then you have the arrays, you have 0.1, 0.9, 0.2, 0.8, 0.95, 0.05. So for I, doc in enumerate the docs now. Then the score, you have NP dots, you have all of this going, and you print the score. So you have 0, 0.2195, 1, 0.3481, 2, 0.9983. So the closest, the most correlate, the most similar is the one with 0.99. And then it retrieves that and gives you your information. So that's the idea of uh, uh, that's the idea of retrieval augmented generation. So we have that. The highest score corresponds to the most relevant document. This is the score, this is the core mechanism behind semantic retrieval systems. That's what you have behind uh, semantic retrieval systems. That's talking about retrieval augmented generation. Okay, so we then go on to talk about vector databases. Embeddings are stored inside vector databases. So as you you know, of course, whether it is for the documents that are being used or your query. So embeddings are stored inside vector databases. Examples include the Pinecone, the Weavier, the Milvus, and the Feist. Their job is to quickly answer which vectors are nearest to this vector. So this operation is called nearest neighbor search. In machine learning, right? We have this k-means nearest neighbor, and you have things like that. Then you have vector arithmetic, right? One remarkable property of embeddings is vector arithmetic. So you can easily subtract and add. So classic example, king minus man plus woman is equal to queen, right? So relationships become directions in vector space now. So a king, you're talking about kingship, and it's not about a man, but it's about a woman, then that means that you can approximate that to a queen. That's a vector arithmetic for unembedded information like that. So imagine relations becoming directions in vector space. So king, NPRA 87, man 21, woman 25. So, and then we say queen is king minus man plus woman. So if you print queen now, you end up getting this 811 like this, 811. So that's king minus man plus woman. That's 8 plus 2. 8 minus 2, 6 plus 2, 8. Then 7 minus 1, that is 6 plus 5, 11. So you have that. So the output is 8, 11. So the nearest length vector may correspond to queen then, right? It corresponds to queen. So this demonstrates how semantic relationships can emerge geometrically. So you see, we are turning words to coordinates like our title for this video uh, explains. So the question now is why high dimensions work. A two-dimensional space is limited, for instance, so thousands of dimensions provide room for many concepts. So advantages include better separation of meanings because sometimes one word can mean two, three, four, five different things. Then you have richer representations. You have less overlap between concepts. You have improved improved retrieval quality, and modern embeddings commonly use hundreds of thousands of dimensions. So for the limitations now, you have embeddings are powerful but imperfect. Common issues include bias. So biases present in training data may appear in embeddings and you have ambiguity. Different meanings can still overlap. Then domain shift. Medical language differs from legal language, so there are domain issues here and there. Then you have language in new words and meanings emerge over time, right? So, but of course, people keep making progress with these things, right? So modern embedding pipeline, a typical production system, you have a user query, and then once a user sends a query to a generative AI, there's a tokenizer. What the tokenizer does is to break up the query into tokens, and then there's an embedding model that embeds the tokens, and then all of that. So the embedded tokens are then converted into vectors, stored in the vector database, and then a relevant document is identified, and then we have a language model that then produces an answer. So every major stage relies on vector representations all the way, vector representations. So the big picture is that the fundamental insight of modern AI is that meaning can be represented as location. So words can become locations, words become vectors. And sentences can become vectors, documents can become vectors, questions can become vectors. So it's more like you have words that are broken into tokens. The tokens are embedded, they are assigned numbers, right? They are assigned numbers, they are assigned dimensions, and then those dimensions are stored as vectors, and the vectors are stored, they are made as vectors, and vectors are stored in vector databases. So you also have your own questions becoming vectors. So once language has been transformed into coordinates, AI can then measure similarity, uh, which has something to do with distance, like distance in meaning, that having converted the words into numbers, then you can retrieve knowledge, you can cluster concepts, you can search semantically, you can generate text, and of course, answer questions. Modern language models are at their core systems that learn and manipulate vast geometric spaces of meaning. So we have that. Then now we are on to the practice problems. They are mostly story this time around. Uh, so we have practice problems. First of all, you can see 1 to 10 here. First question, explain why an AI system cannot directly work with raw words and instead requires numerical representations. Of course, machines don't understand words. They only understand numbers. They only understand numbers for sure. So we have to go through the process of making that possible for them. Then, um, a vocabulary contains 50,000 unique words. What is the length of the one hot vector representing each each word? Of course, the length will be 50,000, So because every word for one hot encoding, right? Each word, the first word will be 1 and 49,999 zeros. The second will be 0, 1 and 49,998 zeros, and so on and so forth. Okay. So here I'll be dealing with just two of these questions. I'll be dealing with problems 14 and 20. So now the second half of the questions now, you have describe the role of gradient descent in learning embeddings. We've talked about that. Problem 14, why is semantic search often more powerful than keyword search? Okay. Because semantic search goes beyond just the surface meaning of the word to the surface idea of the word to what it really means in the context in which it is used. Then question 20, describe the complete journey of a user query from text input to generated answer in a modern AI system, including tokenization, embeddings, retrieval, if applicable, and generation. Yeah. So with this now, you can really know what's happening when you prompt a when you prompt an AI model. Okay, so let's go starting with problem 14. Problem 14. Question, why is semantic search, why is semantic search more more powerful than keyword search? Okay, so we can simply say that this is how it goes. Keyword search Keyword search looks for exact words or phrases. Keyword search looks for exact words or phrases. So an example of that would be this. Example, imagine you have a query. You have this query. How how do stars collapse into black holes? That's your query. How do stars collapse into black holes? You have that query. And then you have a document. You have a document like this. Massive stars, massive stars eventually form singularities. Eventually form singularities. So that's a document right there that seems to correspond with your query. So now we see then that a keyword, a keyword search, a keyword search may fail, may fail because the document does not the document contain does not contain the exact phrase. The exact phrase black holes, right? Doesn't exactly contain the exact phrase black holes, which we have here. Now, with that in place, we then look at the advantage of semantic search, right? So we see that semantic search works differently from keyword search. Semantic search works differently. Okay. So, and how does it work? The first step it takes is to step one, it will convert convert the query into an embedding vector, into an embedding vector. Say big Q goes to Q like this. And then in step two, it converts every document, it converts every document into an embedding vector, into an embedding vector. So something like D1 goes to document 1, D2 document 2, D3 document 3. So because it needs to understand the concept, the context, and then we have step 3, compute, it will now compute similarity scores. Compute similarity scores in the sense that, you know, you have this embedding now. Q has become small q, and each document, big D has become small d. So computing similarity scores now means you get the similarity between Q and each DI. You know, this Q now, so it will now be checked against D1, D2, D3 to pick which one it's most similar to. So we have these DIs in general. So then we can then say the document, the document about the document about singularities, the document about singularities may receive a high similarity score, a high similarity score because its meaning, is closely related, is closely related to black holes. Therefore, semantic search retrieves information based on meaning rather than exact word matching. Exact word matching. Because exact word matching is prone to mistakes if the context is not understood. So if I talk about bank, right? If you are using keyword search, it can just give me Riverbank instead of bank account. So, but semantic search will try to understand the context and know what's up, what to give, right? So, in conclusion, we can say, in conclusion now, in conclusion, we can then say that semantic search is more powerful, because it can find conceptually related information, even when the exact words, or rather, even when the exact keywords are absent. Like that. So that takes us to problem 20 then. Problem 20. So problem 20 says to describe the complete describe the complete journey. Describe the complete journey of a user query from text input to generated answer. And this would be an interesting question for everybody who uses generative AI. So describe the complete journey of a user query from text input to generated answer in a modern AI system, including tokenization, embeddings, retrieval if applicable, and generation. That's like giving you the answer. That's why it's called generative AI, right? So let's go ahead and do that step by step. Solution. So consider the user query. Consider the user query. Consider the user query. What causes black holes? Okay. What causes? Okay, this is not what I intended to use. What causes black holes? What causes black holes? Okay, what causes black holes? So in step one, we have tokenization. So the first thing, the query will be tokenized. Tokenization, so such that the text is broken, the text is tokens, broken into tokens. So for instance, you have the following. You have what? Okay, maybe I should write this first. What? That's one token. Causes, another token. Black, another token. Holes, holes, that's another token. And then question mark, another token. So that's something. So these are the tokens now into which your query has been broken down into. So once that is done, then the next thing is the tokens are converted into numerical IDs. Okay. The tokens, the tokens are converted into numerical IDs, numerical IDs, right? Such that you have something like 523 1847 1847, right? Then 4510 18763 and 30. So you have numerical IDs like that 12345, right? 12345. So each word now has a numerical ID. So with that done, the step two now is about embeddings. So step two, so first step is token. Once you type in the query, first step is tokenization. Second step is embeddings. So embedding now. So each token ID then is converted into a vector. So like you have 523 becoming vector 1, 1847 becoming vector 2, then 4510 becomes vector 3, 18763 becomes vector 4, and so on and so forth. Okay. So these vectors capture semantic information. These vectors capture semantic information. With that done, we move on to step 4. So tokenization and first step, you have tokenization. Second step, you have embedding. Now step 3, sorry. Step 3. Yeah, step 3. Step 3 then is about transformer processing. Transformer processing. Okay, for transformer processing, you see that the transformer examines, the transformer examines relationships, relationships among all token vectors. For example, you see that black black influences holes, right? Black influences holes, black holes. Then we can then see that causes causes influences influences the interpretation of the question, because you're asking for a cause now. So because it's on, so the cause can then say, okay, because you're looking for causes influences the interpretation of the question. So the model produces richer contextual embeddings, richer contextual embeddings, such that we can then have, say, Vi going to Hi, where each vector goes to Hi, right? Where represents, H sub I represents a context-aware embedding, a context. So each vector is mapped to a context-aware embedding. Okay. So with that done, we move on to step 4. So we have step 4. In step 4 now, we talk about RAG. Step 4 now is about retrieval. So retrieval, maybe RAG systems, for instance, you have RAG systems. So if the system uses RAG is retrieval augmented generation. Retrieval augmented generation. Retrieval augmented generation, that's RAG. So the query embedding, is used to search a vector database. A vector database. So imagine you have a query vector. Query vector to be something like Q, and then you have stored documents, just like what we saw in the last question. You have stored document vectors. Stored document vectors are like D1, D2, D3, and so on for the different documents. Okay. So then the computes, system computes similarities, and retrieves the most relevant documents, For instance, so we can have an example like this of a retrieved document. Example, retrieved document. Example, retrieved document can be something like this. Black holes form when massive stars collapse under gravity. Black holes form rather. Black holes form when massive stars, collapse under gravity. Okay. So this is what is generated. So that's an example of that. Of a example retrieved document now. Retrieved document, not generated yet. And that takes us to step 5, talking about generation. So step 5 now, where we now deal with generation. So step 5, where you now have generation. So generation can be done using the contextual embeddings, the retrieved information, the retrieved information, the learned model parameters, the learned model parameters. Then the AI predicts the next token, predict the next token repeatedly. I mean, like we saw in the very first few sets of videos. So we can have this example, right? Say example. So example can be you have black, black. Then next holes, next black holes form when black holes form when massive massive stars so and that keeps going and so on and so on until a complete answer until a complete answer is produced. So you can then see that the final pipeline is something like this. Final pipeline now. You have user query, user query. So from the user query, we have tokenization. Tokenization is breaking the text of the query into smaller words called tokens or smaller word chunks. It can be full words or chunks of words. So user query tokenization. Then next, each token is assigned a token ID. So you have token IDs. So then based on each token ID, we then have, so each token is now embedded. So we have embeddings. Then after embeddings, we have transformer processing, transformer processing. So from transformer processing, we go to an optional part now. This is optional, and that is option. This part is optional, and that is the vector retrieval. So vector retrieval is optional. So afterwards, we can move on to next token prediction. So you get the first, the next, and the next, and the next token prediction. And then finally, you have your generated answer. Generated answer. Generated answer. And with that in place, we can go to the conclusion. So in conclusion, then we see that, so we see this thing, how it flows step by step. So a modern AI system transforms text into vectors, into vectors through through transformers, through transformers. Okay. Then optionally retrieves relevant knowledge, optionally retrieves relevant knowledge using vector similarity, using vector similarity, and then generates generates an answer one token at a time. So that's how that goes. With this, we come to the end of this interesting video, which talks about how AI turns word into coordinates. So machines don't understand words, but they understand numbers. So we turn our human words, human language into numbers, right? That machines can then understand. And that is done, other processes follow, and then we have our results generated back to us. So you want to go further to think about this. So look at the questions 1 to 10. You want to try your hands on them. Just try to answer them to yourself and see if you really get the gist. And then you can check, you can rewind the video to see if your answer is right or not. So thank you so much for listening. You have questions 1 to 10 here and then 11 to 20. Let me know how helpful this is for you. And if there's something else you'd like to be able to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. What if you have not? Why not just go ahead right now and do that? Subscribe to the channel, hit the notification bell also, so that you can always get alerted each time a new video is released. Then, of course, ultimately, don't forget to comment, like, and share so that other people can have access to the great content I have going on here. Then, if you want to become a member of this channel, you can click on join. That gives you some special privileges that you are going to see as you click on join. So again, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.